Hi, this is Stan Lyle with MasterMath. During the lesson, you're going to come to some You Try It slides where you're asked to do problems that relate to the lesson. Hit your pause button, try the problem, and then hit the forward key to move on to the answer. I hope you have a really good time today. Today we're going to be talking about solving inequalities with addition and subtraction. And before we get into that, let's just review what inequalities are all about. Let's say I've got a number x, a variable x. I don't know what x is yet, but I want to know what the relationship is between x and 3. Well, there's several ways that x and 3 could be related. For instance, you could say that x was greater than 3. That would mean that any number greater than 3 qualified as a potential x. 4 could be x, 5 could be x, but 3 couldn't be x because 3 is not greater than 3 and 2 is less than 3, so 2 couldn't be x. So, I could say that x is greater than 3. I could also say that x was greater than or equal to 3. In this case, 3 would qualify as a potential x because 3 is greater than or equal to 3. 3 is equal to 3. 4 again would qualify, but 2 wouldn't qualify. I could also say that x is less than 3. And that way, any number less than 3 could potentially be x. 2 could potentially be x. Minus 5 could potentially be x. And I could also say that x was less than or equal to 3, in which case 3 would qualify because 3 is less than or equal to 3. And minus 2 would qualify because minus 2 is less than or equal to 3. But 4 wouldn't qualify because 4 is not less than or equal to 3. Now again, just in reviewing, if you forget what these symbols mean, it's pretty easy to recall. And the rule is the bigger end of the symbol goes towards the bigger number. And the smaller end of the symbol goes towards the smaller number. So if I've got x, 3, the bigger end or the open end is facing x, so it's telling me that x is a bigger number than 3. In this case, the bigger end is towards the bigger number, so it's telling me that 3 is bigger than x, or x is less than 3. And the other symbol that you've got to add to this equation is this little underline that we put under both the greater than or the less than symbols. And all that means is that it's going to be greater than or equal to. It's like half an equal signal, and it just signifies that x could be also equal to that number. You know, I said this before, and I hope it makes sense to you, but math is just a way of modeling the real world so that you can manipulate it and understand it better. And inequalities is exactly an example of that. You run into inequalities in the real world all the time. And you're going to need to translate those into math in order to be able to manipulate them. Let's think of some examples that relate to a movie theater. If you went to a movie theater, you might discover that you must be at least 13 to enter the theater. Or they might tell you that fire code requires that attendance be less than 400 people. Or someone might tell you that people older than 16 wouldn't enjoy this movie. Well, those are all examples of inequalities expressed in English. Can we express those in math? Sure we can. On that last one, people older than 16 wouldn't enjoy this movie. If we let P equal people who wouldn't enjoy the movie, then we could say that P is greater than 16. people who wouldn't enjoy the movie are greater than 16 years old. How about the fire code incidents? What if we let A equal the attendance? Then we could say that A is less than 400. The attendance has to be less than 400. How about the 13-year-old requirement? Let's say X equals the people allowed to enter the theater. We could say that X is greater than or equal to 13. Well, in that last slide, we had three inequalities that we listed. P is greater than 16, A is less than 400, and X is greater than or equal to 13. How would we put those on a number line? And this is kind of important because later when you get into algebra more deeply, you're going to have to graph equations, and you're going to have to basically understand what these how to graph these equations. So let's start with a simple number line graphing, and we'll start with X is greater than or equal to 13. If I want to graph that on a number line, what I'm going to do is draw a circle at 13, and I'm going to fill it in, and then I'm going to draw an arrow in the direction of numbers that are greater than 13, and that symbol then represents X is greater than or equal to 13. What about A is less than 400? Well, again, I get a number line and I draw a circle around the 400. But I don't color it in because the 400 is not included. Up here, we've painted red over the number 13, and that means that 13 is part of this continuation of the numbers that's greater than 13. It's numbers 13 and greater than or equal to 13. But in this case, 400 is not included. A is less than 400. So we don't want to include A. We don't color it in. We put a circle around it, and then we draw the arrow in the direction towards the smaller numbers because A is less than 400. And you can see that all these things on the blue line qualify for this. I mean, 200 is on that blue line, and 200 is less than 400. But 500 is not on the blue line because 500 is not less than 400. How about P is greater than 16? Well, the trickiest part is to remember that this is not P is greater than or equal to 16. This is P is greater than 16. So I don't want to color the 16. I want to avoid coloring the 16. So I'm going to draw a circle around it, and I'm not going to color the 16 because it's not part of this solution set. And then I draw an arrow towards the larger numbers because P is larger than 16. Well, now let's do some algebra. And now let's get to the meat of this subject. The subject today is solving inequalities with addition and subtraction. And you know how to solve equations with addition and subtraction. Well, you're going to discover that solving inequalities with addition and subtraction is exactly like solving equations with addition and subtraction. In the next lesson, we're going to talk about solving inequalities with multiplication and division, and that's a little different between equations and inequalities. But in terms of addition and subtraction, all the rules are just the same. Let's look at an example. Well, you know that 200 is less than 400. Well, what if I added 5 to both sides of this inequality, and I changed it to 205 is less than 405? Is that true? Is 205 less than 405? Absolutely. So what we've shown is that I can add a number to both sides of an inequality and not change the inequality. I could also subtract a number from both sides of the inequality, and as long as it was the same number I subtracted, the inequality would still be true. Well, what if instead of 200 is less than 400, I add x, a variable, is less than 400. Could I add 5 to both sides of that? Sure I could. I could say x plus 5 is less than 405. Well, that's useful, but now let's look at another example that's a little more related to solving inequalities. Let's say that we knew that x plus 15 was greater than 65. How would we solve that? Well, if it was an equation, it'd be real easy. I know how to do this. I'd just subtract 15 from both sides of the equation, and I'd have x equals 65 minus 15, or 50. With an inequality, it's exactly the same. I can subtract 15 from both sides of the inequality, and I won't affect the inequality. X plus 15 minus 15 is greater than 65 minus 15, or x is greater than 50. How about this one? Z minus 8 is less than 22. Well, as long as I'm adding and subtracting, and I do the same thing to both sides of the inequality, I'm not going to change the inequality. So I can add 8 to both sides of this inequality, and z is less than 30. Well, we just solved an inequality. Z minus 8 is less than 22, and we solved it and concluded that z was less than 30. Did we do that right? Well, I think we did. That was a pretty easy one, but at some point you're going to deal with some more complicated inequalities, and you may want to test them to make sure you did it correct. How do we test this? Well, what we proved was that z was less than 30. If we took a number less than 30, let's say 29, and substituted it for z in the inequality up above, it ought to hold true. Let's try that. Z equals 29. So instead of z minus 8, we'll write 29 minus 8 is less than 22. And 29 minus 8 is 21, and 21 is in fact less than 22. So, for numbers less than 30, this inequality remained true. How about for numbers that are not less than 30? Well, we could try 31. 31 is not less than 30, but 30 is also not less than 30. 30, if I put 30 in there for z, I'd have 30 is less than 30, and you know that's not true. So if I put 30 up here in z minus 8 and make it 30 minus 8, it better not be true that that's less than 22. Let's try it. Z equals 30. 30 minus 8 is less than 22. Well, 30 minus 8 is 22, and 22 is not less than 22. 22 equals 22. So we proved that z is less than 30 is a correct solution for z minus 8 is less than 22. Solve this inequality for c, and then draw it on a number line. C plus 16 is less than or equal to 16. Well, if instead of a less than or equal sign, we had an equal sign, you'd know how to solve this real easily. You just subtract 16 from both sides of the equation, and you'd have c equals 0. It's the same as long as you're adding and subtracting, whether you've got an equal sign or an inequality sign. C plus 16 is less than or equal to 16. I can subtract 16 from both sides of the equation, or both sides of the inequality, and then it's going to read C is less than or equal to 0. Now, how would I graph that on a number line? Well, first I'd need a number line, and then I draw a circle at 0. 0 is our solution. So I want to draw a circle at 0. And our solution includes 0. So I want to paint over that 0 so it's part of that green mass that identifies our solution set. So I fill in the circle, and then we're less than or equal to 0. So I want to show numbers less than 0. So I draw my arrow towards the negative numbers, and that'd be how I drew that inequality on a number line. Does this number line correctly describe the statement, the temperature in Baltimore has never gotten below -5 degrees? Well, let's think for a minute. The temperature in Baltimore has never gotten below -5 degrees. Is that a less than, a greater than, a less than or equal to, or a greater than or equal to situation? Well, what it's telling us is the temperature in Baltimore has never gotten below that. That means it's always above that. So the temperature is going to be greater than -5. But would it include -5? Is it temperature is greater than -5, or temperature is greater than or equal to -5? Well, that's easy to do. If you put -5 into the equation for temperature and it still makes sense, then we want to include -5. Is -5 below -5? No, -5 isn't below -5. -6 is below -5. -10 is below -5. But -5 is not below -5. So we want an greater than or equal to sign. And then we want to draw this to include -5. But what we drew was a circle, and we didn't paint over the -5. So it excludes -5. It shows that it's numbers greater than -5, but it doesn't include the -5. So no, this number line does not correctly describe the statement. Well, in this situation, you want to go buy some sandals, and the sandals are going to cost you $30. And to get down to the shoe store, you've got to spend some money on bus fare, and you've only got $36, and you don't know how much the bus fare is going to be. So what you want to do is write an inequality that expresses how much you could spend for your bus fare, and then we want to draw that on a number line. Think we can do that? Well, I think we can. Then I think the first thing we ought to do is CUCC this. So let's circle the numbers. I've circled $30 and I've circled $36. 30 is what the cost of the sandals are. $36 is how much money you've got. Then I want to underline the question. The question is, what's the greatest amount you could spend on bus fare and still have enough left to buy the sandals? Now I need to give this question a variable name, so let's call bus fare F. So F is the greatest amount I could spend on the bus fare and still have enough money to buy sandals. Well, you can probably figure this out. If you knew that you had $36 and you knew that the sandals were going to cost you $30, how much money would you have left to pay for the bus? Well, you'd have $6. You'd have up to $6. If the bus fare were $7, it wouldn't work. If the bus fare were $5, you'd be in good shape. If the bus fare was $6, you'd have just enough money. So how can I write this as an inequality? Well, just like this. I could say that F was less than or equal to the $36 that you've got minus the $30 you want to spend on the sandals. So the amount of money that you spend for the bus fare has to be less than or equal to $6. And if I graph that on a number line, I'm first going to draw a circle at 6 because that's our solution. And it includes 6. It's less than or equal to 6. So I'm going to paint that in because I want that 6 to be included. I want the paint on that 6 because it's part of the solution set. And then I'm going to draw an arrow down towards 0 because the fair has to be less than 6. Now, I didn't draw it into the negative numbers because I don't think that that's a reasonable range for fares. I don't think anybody's going to pay you to ride the bus. So I only drew that line down to 0. Well, that's our lesson on solving inequalities with addition and subtraction. The next lesson you're going to find a little bit tougher. That's solving inequalities with multiplication and division. But for now, I hope you understand solving inequalities with addition and subtraction, and you ought to go test your skills. Go to www.mastermath.info and download the worksheet on solving inequalities with addition and subtraction. Then try the quiz at Mastermath on solving inequalities with addition and subtraction. And then be sure to come back and study that lesson on solving inequalities with multiplication and division. See you next time.